called as the gravitation. So starting with a new chapter, that is gravitation. So gravitation is defined as the non-contact force. Non-contact force. We have seen till now that what is force. What was our force? Force was defined as the mass into right? And what kind of force is this? This is a attraction force, attractive force which is acting between two bodies in the universe. And there is one line that is in bracket which says that no matter how far, okay, it should be how far, it should be how far, and how far the bodies are. Okay, so here distance is never taken into, like, whatever may be the distance between the two objects in the universe, they will always have a non-contact force of attraction between them, and this is what defined in the term gravitation. Or gravitation is the non-contact force. When this is a force, till now we saw that force was being acted when there was some contact between the two bodies, but our gravitation, it is a non-contact force of attraction. How, what kind of force is this? This is a attractive force. Means the two bodies in the universe will attract each other. Between two bodies in the universe, no matter how far the bodies are. Okay, so this is a non-contact force of attraction. Then the earth attracts or pulls all the bodies towards its center. Now see, we are standing on the earth. See, if this is our earth, if we are standing on the earth over here, we are always attracted towards the center. We are always attracted towards the center of the earth. If we were not attracted towards the center of the earth, we would have flied somewhere else, right? We would not be able to stand still on the ground, which we are now able to stand, sit, walk, and do a lot more activities on the surface of the earth. This is because the earth attracts each and every object towards its center, right? And this force with which the earth pulls the bodies towards it, it's called as the gravitational force of the earth, or the gravity of the earth. This force with which earth is attracting each and every body towards its center is called as the gravity or the gravitational force of the earth. It's not necessary that it only acts between earth and the person standing on the surface of the earth. It is also acting between each and every object. It is acting between each and every object. You can also see in the first paragraph, it is saying that between any two bodies. Here the word any is also used, right? It is the force of attraction between any two objects. Even you sitting in your classroom, say you are sitting on this place A, and there is some board in your classroom over here. So even there is a force of attraction between you and the board. Even there is a force of attraction between you and the friend sitting next to you. This force of attraction is between each and every object of the universe. Okay, now we'll discuss about some characteristics of this gravitational force. See, the gravitational force is action. It is a action at a distant force. That is, it does not need any contact between any two bodies. Means there is no need of contact. It is just action at a distance. It is an action at a distance, and no contact is required between the two bodies. Still now we were seeing that whenever we used to apply the force, there was some contact between the two objects, right? We saw the examples of players playing cricket, footballers kicking the ball, pushing of table, chair, and all that kind of examples in which a contact was required between the two objects. But here, in the case of gravitational force, there is no need of contact. There is no need of contact between the two bodies. It is a contactless force. Now we move on to our next point, which says that the gravitational force acting between any two bodies form a action reaction pair. It always form a action reaction pair, and this action reaction pair we saw in the third law of motion. We saw it in the third law, right? What was that? The action reaction pair will always act on two different bodies, which makes the force conservative, right? Means there is no cancellation of the two equal and opposite forces as they are acting on the two different bodies, right? See, we'll continue the statement. That is, the force exerted by the two bodies on each other are equal in magnitude and opposite in direction. This we also saw it in the third law of motion, that action reaction pair are always equal in magnitude, are always equal in magnitude but opposite in direction. Now, how is this happening? We'll see it by one example. So, if there is some body A and there is some body B. This is our body A and this is our body. Now we have seen that the gravitational force is an attractive force. So B will start attracting A towards it in this direction, and now A will start attracting B towards it in this direction. So this force, say F is attracting B with force F1, and this is our force, say F2. So here F1 is always equals to the force F, but as they are in the opposite direction, a completely opposite direction, so we say that they form a action reaction pair. And this opposition in the direction of the force is always present, means it will never happen that the two forces are in the same direction. They will always be in opposite directions and their magnitudes will also be equal. That we will see in upcoming points. Okay, but till now you should be clear with this concept that there will always be equal in magnitude and opposite in direction. And as we say they are equal in magnitude and opposite in direction, it forms a action reaction pair. So now moving on to our next point. Now the gravitational force is the weakest force in the nature. It is the weakest force. You are asked this question many a times in your exam, so make sure you remember this point. It is the weakest force in the nature, yet it binds the earth within the solar system. Not only earth but all the 8 planets within the solar system, right? Even though it is the weakest, it has a power to control such big planets. And even it is the gravitational force which keeps us bind by the earth. If this force was not there, we would have flight somewhere else. We have discussed it earlier also. So even though it is the weakest force, it has a lot of power with it, right? So moving on to our next point, which is the gravitational force is constant as well as conservative. Say constant as well as conservative. Now the word constant. Now this magnitude is constant at each and every place. Means wherever you will go, if you are measuring the force of attraction at some your home place, say you are at your home and you get some value of this force, the value of this force will be same even at your school or at your some friend's home. it will always be same. And there's one more word which is as well as conservative. Conservative means we have also discussed it in this point number 2 that they always form an action reaction where action reaction pair means equal in magnitude and opposite in direction, and they act on two different bodies. So as they're acting on the two different bodies, they never get cancelled out. And as they never get cancelled out, they are conservative means they remain as it is. There will be no change in the values. They will never get cancelled out. Okay, so this is what means conservative, and constant we have discussed it now. So the next point is the gravitational force between two small bodies is very small. The two small bodies may include uh, you and the furniture in your house, or the pen lying on the table, the books lying on the table, the newspaper, and every other object in your house. They are very small. But on the other hand, it is very large between two large bodies, say the sun and the earth. But when we compare this gravitational force for two large bodies, the two large bodies may be the sun, the earth. So in this case the force of gravitation, the force gravitational force will be very large. I also mentioned it before that even though the gravitational force is the weakest force in the nature, but it still holds the power to bind the earth towards the sun. Not only earth but all the 8 planets, and even the moon is revolving around the earth because of the gravitational force only. Okay, so we'll move on to our next point, which is the universal law of gravitation. So this universal law of gravitation was given by Newton. It was Newton who discovered that there is always a force of attraction between the two bodies of the universe. Any two bodies present in the universe will always attract each other. This was first stated by scientist Newton. Then, according to this law, the attractive force between the two bodies is directly proportional to the product of their masses. It is directly proportional to the product of their masses, and inversely proportional to the square of the distance between them. Now, directly proportional means if the value of one quantity increases, the other quantity will also increase. But when it comes to inversely proportional means if the value of one increases, the other will start decreasing. Okay, so this is what we mean by directly proportional and inversely proportional. Now, writing this law in terms of maths, we write it as gravitational force. This gravitational force F, we also represent this force by F, is directly proportional to product of the masses. Now here the two masses are M1 and M2, and it is inversely proportional. See this gravitational force we represent inverse proportional as F is inversely proportional to R square. So in this case, we write it directly as F directly proportional to M1 and M2 upon R square. And to remove this proportionality sign, see there is this proportionality sign alpha. So to remove this proportionality sign, we introduce one constant. You see this capital G, it was not present in the above statement. So this capital G is our now constant, and this capital G is called as the universal gravitational constant, and the value of G is 6.67 into 10 to the power minus 11 Newton meter square per kg square. This is very important. You need to remember this value in order to solve the numericals based on this concept. Okay, and here the unit is equally important. The unit is Newton meter square per kg square. Then there is a other statement that the law of gravitation is applicable for all bodies. It is applicable for all bodies irrespective of their size, shape, and position. Means what? This universal law of gravitation is applicable for all bodies. It will not change if there is any change in the shape, size, or position. I discussed it earlier in the characteristic part that this force is always a constant force and it is a conservative force. Constant means even if there is a change in the shape and size, but the masses remain the same. What I'm saying, the mass remain the same because it is dependent on the mass. See, you can see this formula that F is equals to capital G m1 m2 upon r square. It is dependent upon the mass but not on the shape and size and position. Position only when the distance between the two bodies are constant. Okay, if you keep the distance between the two bodies constant but you take it to other places, in that case the force of attraction will remain the same. But if the distance is changing, when we change the position, there will be change in the force. Okay, so now we will move on to our next point. There is the importance of universal law of gravitation. Means what does this tell us? That law of gravitation, how and where we can see this, its application. So universal law of gravitation successfully explains several phenomena like the force that binds us to earth. It is the gravitational force which will bind us to earth. It will help us to remain on the surface of the earth. It is the gravitational force. In the motion of the moon around the earth, I also stated it earlier that the moon revolves around the earth because of the force of gravitation between moon and the earth. Then next is the presence of atmosphere around the planet. Now here not only earth is said but all the planets. Every planet has some or the other atmosphere around it. Now it is because, see, if this is our earth and there is some presence of atmosphere around this earth, around the earth there is presence of atmosphere. Now this atmosphere is because of the attraction. The atmosphere is made up of several particles and these particles are always attracted towards the earth, and as they are attracted towards the earth they form the atmosphere. If there was no gravitation there would have been no atmosphere, and with no atmosphere there was no life possible even on the earth. It is not possible on the other planets, but if atmosphere was not there the life would not be possible even on the earth, right? So now we'll move on to our next point, which is the acceleration due to. Now we know that force is equals to mass into acceleration. So this force is also applied by earth on us. That is why we are bound by the earth on the surface of the earth, right? If there was no force between us and the earth, there was no possibility that we were able to stand on the surface of earth. Now if there is some body, any body, it can be you, it can be me, or anything around you, it will have some or the other mass, right? But if there is a presence of force, we need mass as well as some acceleration. So mass we are having. If there is any body, it will have some or the other mass on the surface of earth, and as the earth is pulling it towards the center, there is force. But where is this force coming from? This force is now coming because of the acceleration, and this acceleration is because of the gravitational pull of earth, and we call this acceleration as acceleration due to gravity. Okay, so see, there is the same theory given here, that whenever an object falls towards the earth, acceleration is involved. Acceleration is involved. This acceleration is due to earth's gravitational force. This is due to earth's gravitational force and is called as acceleration due to gravity, and this is denoted by a small g. Okay, so as this is, the word says that acceleration or g is nothing but the acceleration only, which we saw in the motion. Okay, so its SI unit will also be meters per second square. It was same for the acceleration in the motion chapter, and it is also same over here. Wherever we will say acceleration, it may be because of some motor, because of some force, or because of anything. Whenever there will be action, its SI unit, acceleration, its SI unit will be meters per second square. Then it is also vector quantity. It was vector quantity in motion as well as vector quantity over here also. And we know that the gravity will have some or the other acceleration, and it will have some magnitude. And now what about its direction? Its direction is towards the center of the earth. We got to know about the magnitude, and now its direction is always towards the center of the earth, right? Then it is saying that the value of g means the acceleration due to gravity, changes slightly. It is not a major change, it is a slight change. Slight means very small amount. It changes slightly from place to place, means whenever we change our place, there will be a slight change in the value of g. So this value of g is taken as 9.8 meters per second square. This is again a very important point, that the value of gravity is taken as 9.8 meters per second square. 9.8 meters per second square for practical purpose, means wherever the value of g is involved, we mostly take it as 9.8 meters per second square. 9.8 meters per second square. Or we can also approximate it. We can also approximate it with value 10. With value 10 meters per second square. Okay. So this acceleration due to gravity, its value is taken as 9.8 meters per second square, or we can also approximate it to 10 meters per second square. Its SI unit is meters per second square. It is a vector quantity, and its direction is towards the center of the earth. Now, we have also discussed one point over here, that the value of g changes slightly from place to place. But how does it change? Now, that is what we are going to discuss it over here. That is variation in the value of g, means how the g will change. when we'll change the position of the object. Now, the first case is outside the Earth's surface. Means, if this is our Earth and there is one person standing over here, and this is the center of the Earth, and from the center of the Earth we'll have some radius. So, this let this radius be capital R, and the mass of the Earth be m1, and this mass of this person be m2. We'll consider it as m2. And now we know that according to the universal law of gravitation, our force F is given by capital G, that is the gravitational constant, capital G into m1, that is mass of Earth, and m2, that is the mass of the person standing on the Earth, upon r square. R square means the distance between them. So now this is the general case. But what if now we calculate the value of G above the surface of Earth? Means now we are at some height over here, and say this height is of h meters, and this distance, the distance between the Earth, center of the Earth and the surface of Earth, that is the radius, is r. It will never change, it will remain the same. But what we have changed is the distance between our object and the center of the Earth. And in this case, our force, say consider it as the force F dash, that is our new force, that will be our G. It is a gravitational constant, so it will never change. It will be m1, that is the mass of the Earth, and m2, that is the mass of the person or the object, upon r square. It is r square. R square means in this case it will be r. The total distance is r plus h. Now the total distance has increased to r plus h, and we'll take the square of this complete bracket, r plus h whole square. So we'll write it as, say, equation 1, this as equation. Now if you see that we have the G m1 m2 in the equation 1 and equation 2 as well, right? In the numerator, if you check, there is G m1 into m2 in equation 1 as well as in equation 2. So from equation 1, say from equation 1, we get that the value of G into m1 into m2 is equals to F into r square, F into r square. So now this we, in the equation 2, we will now substitute this value of G m1 m2 with F into r square. So we get our new equation as F dash is equals to F into r square upon R plus H R plus H whole square. Now, as we will go on increasing the value of H, means as we will start moving away from the surface of the earth, the value of new denominator will start increasing, and as this value will go on increasing, or this the force will go on decreasing, because it is inversely proportional to each other, right? So from this, we come to know that when we start moving away from the surface of Earth, when we will start moving away from the surface of Earth with the increase in the height, as the height will start increasing with the increase in height, there will be decrease in the force of attraction. There will be decrease in force. When the height will increase, there will be decrease in the force. Okay, so for clear that, and the new force, that is F dash, is calculated using this formula, where F is the original force. The original force will change with the this value, whatever we are having in this box. If we are supposed to calculate the new value of force, if the object is changing its position away from the surface of Earth at height h. Okay, so for that purpose we have this formula, and now we'll discuss inside the Earth's surface. Now we have seen that the value of the force on the surface of Earth is given by F is equals to G m1 m2 upon R square. G m1 is our mass of Earth, and then m2 upon R square. Where R is the radius of the Earth. This was available when we were on the surface of the Earth, and our Earth is almost a spherical body. Our Earth is almost a spherical body, and the volume of the sphere is given by V equals to 2 by 3 pi r cube, right? So, and if the density of the Earth is given by rho, and we know that the density, the formula for density is equals to mass upon volume, mass upon volume, and we are supposed to calculate now this mass. So from here we get that the mass is equals to rho into volume, or the volume into density, volume into density will give us the mass, and from here we have the formula for V, that is equals to rho multiplied by 2 by 3 pi r cube. 2 by 3 pi r cube. And in this case, this r is same as that of the radius of the earth. So instead of writing this small r, we can also write, yeah, capital R. So this is our mass of the earth, and using this mass of earth in our